Welcome back, everybody. What we're talking about today is k-mean clustering. Okay, and really we're going to talk about the theory as usual. Then we're going to get into some coding examples. Okay, so what is k-mean clustering? Okay, and in this video series, what we've done so far is we've just talked about supervised learning. But k-mean clustering is unsupervised learning, and that means that the data is not labeled. Okay, and I want to make a good point about this. We're going to use a sample in our coding section of this video where we do have some categories between age and square footage. Okay, but it's not labeled in the traditional sense that you're thinking about. Okay, so the thing with k-mean clustering is it divides similar objects into clusters. Okay, and then it divides dissimilar objects into different clusters. Okay, so this is really about making clusters of things that are similar in some sort of a way. Okay, and so what is the k in k-mean clustering? What is that? And k is the number of different clusters you want to divide into. Okay, very simple, and once you see it, it'll make sense to you. Okay, and the good thing is we can actually optimize k, and it's not that difficult to do. And we'll see that with the example as well. We'll consider whether or not we want to optimize k or not. Okay, so, we're going to take this example here. Okay, we've got baseball, and in baseball, you have a pitcher right there, and you have a batter who hits the ball. That's the goal, to get the number of runs. So in this theoretical example, okay, we want to identify the batter and the pitcher. Okay, and the data contains the runs and strikeouts over 9 innings. Okay, so this is our theoretical example. The pitcher will have more strikes and the batter will have more hits. Okay, so that's kind of the way this is sort of broken down. And we want to cluster that. I know you probably want to sit there and watch the baseball game. I get that. But if we look at this on a plot, okay, we can see that if we start at the origin, the higher we go up the y-axis, you see that the batters are getting more runs. And if we stay on the x-axis, as we go, the pitcher is getting more strikes. So just kind of naturally, you can see that there's this cluster forming. Okay, so if we divide into 2k, okay, so the number 2, we say that k is number 2. What happens is we can look at our plot again, and we can create the first cluster here. And this is based on runs versus strikes, right? So the batter with the higher runs and lower pitcher strikes, okay, in this cluster 1. And then in cluster 2, what we're seeing is batters with the lower runs and higher pitcher strikes. Okay, so that's what we're seeing there. So where do we start with this? Now, remember our good friend Euclidean distance. Okay, so we talked about this last week with k nearest neighbor. So we've got the Euclidean distance formula to find the distance between 2 points in the plane with coordinates x, y, or a, b, right? So this was our example from last time. Okay, d represents the distance between those 2 coordinate points. Okay, so when we look at this, we have these 2 sort of naturally occurring clusters, right? Now, the first step that we have to do is assign something called a centroid. Okay, and we're looking for really the center point of the 2 clusters. Now, when you first start off, it's a random centroid. Okay, and the next step that you want to do is find the Euclidean distance to determine which centroid is closest to each point. Okay, now this is a little bit different than what we did with k and n, in that we have to approach this from a different point of view. We have 2 distances to measure. Okay, what you have, the first one and the second one. Okay, so you've got a Euclidean distance for the first centroid and one for the second centroid. And what you're doing is you're making this comparison. And the comparison is, you can see here, I'm measuring the Euclidean distance from my centroid to a point, any point. Then I'm using my Euclidean distance from the other centroid to the same point. Okay, and this continues to repeat. So you can see that this centroid is measuring the distance to this other point, and then it just continues. So this cycle continues, and whichever is less is the winning centroid for that data point. Okay, so you can see that this is how it finally starts to break up. Okay, so that the centroid is now kind of being assigned all of those points over on the left in orange, and the ones in purple are the ones on the right. Okay, so you have to understand that centroids are reassigned to the to an optimized location. Okay, so we started off randomly assigning the centroids. Okay, it was perfectly random where we put it. But as we go, we start to narrow down where is the actual absolute or optimized centroid location within our data points. Okay, and so we continue this until both centroids and data points stopped their assignment. Okay, once they stop that, it's actually called convergence. So we want that convergence. Once we get to convergence, we can stop moving all of the pieces around on the table. Okay, so there's 4 types of distances that we can have. Okay, there's Euclidean, there's Manhattan, there's squared Euclidean, and finally cosine. Okay, and these determine similarity between 2 elements, and they influence the shape of the clusters. But for the most part, we're just kind of sticking with Euclidean. And in fact, when we do the code, we're not really even going to specify Euclidean. The Python libraries that we're going to use are going to do all that stuff under the hood. But it's important to me that you understand kind of what's going on in the background. So each one of these have different formulas. Euclidean and squared Euclidean are very similar. Cosine gets a little more complicated, and Manhattan isn't too bad either. But for the purpose of this video, I'm not really going to elaborate on the mathematical equations, especially in the code. We don't even see it. Okay, so I want you to understand there are 2 types of clustering. Okay, the first one that we have is hierarchical. Okay, and I could have tried to explain the agglomerative. It's hard to say, agglomerative and divisive. It doesn't really matter, to be honest with you. What's important is that you understand there's 2 types of clustering. Okay, and then the other one is partitional clustering. Okay, very similar. This is what we're doing this in our example today. So you've got k-means, which is 1, and you've got fuzzy c-means. Okay, and we're going to focus today on k-means, not fuzzy c-means. But basically, fuzzy c-means is just kind of a method of doing this with an overlap. And you can see it's like a Venn diagram in the middle. There is a cluster in the middle. Not important for what we're doing today. Okay, so examples of using k-mean clustering could be something like academic performance, wireless sensor networks, search engines, stuff like that. Like, that's kind of the application to this. I would love to see some other things, because when you talk about, let's say, the world of algorithmic trading, okay, that might be an interesting way to do unsupervised learning, where you're looking for the trading charts to actually reveal what the pattern is. But I don't necessarily think that k-mean is probably the best use case for that. Okay, but there are many other use cases where we would want to use k-mean clustering. One big place that it's used is in computer vision, when you're dealing with colors and stuff like that. That's another use case for this. Okay, so let's kind of look at how this k-mean clustering works. Okay, we have our start point, that the very beginning of what we're doing. Then we're going to make a sort of preemptive determination of the value of k. And really what I'm saying is you're kind of going to look at the data, see if you can intuitively come up with something, and then just kind of take an educated guess. Then we're going to do, we're going to measure that distance. Okay. And you can use one of the 4 options here. Okay. Then we're going to do, and so this, we group based on that minimum distance, like I just showed. Okay. With the centroids and all the different points. Okay. And then the next thing that we're going to do is reposition the centroid. Okay, so that's part of the whole, algorithm. But the beauty is that centroid, that repositioning is going to get taken care of from the library files. Okay, so that we're not physically going to be doing that so much. I do want to say there is one thing that we'll talk about today, that is scaling out our scatter plot, so that these it helps with repositioning the centroids as well as all of our data points. Okay, because ultimately we want to get to this convergence. Okay, so final centroid positions. So that's a really important thing. And we can only do that, when we've done the scaling, we've repositioned everything, and we have stable clusters that we're selecting. And, if we don't have those stable clusters, then we have to go back sort of in our algorithm and continue this cycle until we get to convergence. Okay, so when we look at, making k-mean clustering work, there's this idea of the elbow method. Okay, and so when we say that k is referred to as the number of clusters. Okay, and I said that we kind of guessed on that in the beginning based on some educated intuition or whatever you want to call it. But we can sort of optimize this with our elbow method. And we have this thing called within sum of squares. Okay, so WSS. And so the sum of squared distances between each data point, okay, and then its centroid. Okay, so here's the big scary looking formula. Not that bad. The beauty is we don't actually have to code this, right? And so we've got our first data point 1, which is xi, and then ci, which is the closest point to the centroid. And if you're interested in the mathematical equation to this, sort of here it is, and this is what it represents. But ultimately, in our case, we want the software to do its thing, do all the heavy lifting for us. Okay. And the good thing about this is that it does find the optimum number of clusters that can be formed for a given data set. Okay. And you'll see in our coding example that, we'll do this at the very end, just to kind of confirm what we visually already understand is true based on our scatter plots. Okay. And you can use this really as a confirmation. Okay, so early on in your code, you can use the elbow method if you're really not sure. Okay, so it's a good thing to know about and to be aware that the elbow method is going to help you optimize your number of clusters. Okay, but in our coding example, the sample size is so small that we're really only going to stick with 3, and that's going to be good enough. But as you'll see, we can actually optimize that if we want. Okay. So when we look at this, what's happening is we're plotting our elbow, and you can see on this graph that a couple of things happen. We see a low change in values if WSS after k equals 2. Okay. So if I go and grab the laser, you can see right around in here. Okay, this is sort of the determining point here. So what we're going to do is just, in this particular case, we're going to be satisfied with 2 clusters. That's really all that we need to have, is those 2 clusters for this particular outcome. Okay, because 3 is not appropriate the way that is. We want to see that slow change in value, okay, along our number of clusters, and we're not really seeing a significant change in value along the WSS. So really what we're saying is the closest one sort of the median or the mean between the two is somewhere around this 2. Okay. Had that been closer to the 3, we probably would have gone with the 3. But in our example, this is good enough. And you'll see with the code, we end up choosing 3 because it is the most appropriate. Okay, so let's get over to Anaconda and open up a Jupyter notebook and start coding this out. In the example that I have here, we've got the names of people. Keep in mind that's a string. And then we've got the age of people here. And this is the square footage of apartment or home that they live in, whatever their residence is. That's the square footage that they live in. And it's based on age. Okay, so what we want to do is kind of take these, this sample set. It's not very big at all. It's only 30 samples, actually 29 if you count the title. So it's a very small sample. But based on this data, which is unsupervised, what we actually want to do is kind of put these into a cluster. Like, so for example, maybe if we had a really large sample size, we'd be trying to determine what region of an area that they lived in. Okay, so for example, maybe this data could reveal that they lived in and around, say, the Greater Toronto area. So based on this data, we can put these people into clusters. And that's what really we're going to try to do in this example. So if I am trying to sort of develop some characteristics of the people in these different groups, I can really quickly look at the data, right? And you can see that from this data, the younger the person is, in a lot of cases, the smaller the square footage of places that they can, that they live in. It doesn't necessarily mean that that's what they can afford. It just suggests that if you're younger, you're in a smaller house. That's all it does. It doesn't really tell you the reason why. And you can see here, you know, upper 35, you can see larger square footages that they reside in. The 20s all seem to be in the same sort of ballpark, in some 30s. Okay. Again, you can see a couple of samples where 40s, people in their 40s are living in smaller spaces, and then some people in their 40s live in larger spaces. You've got one here, 28 years old, has 1,000 square feet compared to maybe other people in their 20s and early 30s. So the data is somewhat randomized. Like, you can look at that data right now and start to mentally visualize some clustering. Okay. So this data is age underscore sqft.csv. So it's a CSV file. Okay. So I'm going to call this one k-mean age sqft. Okay. So we'll rename that. So the first thing I need to do, obviously, is do all my imports. And the first line here, I hope you can see it. Maybe I can zoom in a little bit more. Okay, that's a little better. So from sklearn.cluster import k-means. Okay, and obviously you know the way that this is working is if I do a capital K and then I capital K, and then I hit my tab and it'll actually come up. So you know that I'm off to the right track. So, you know, typically we do pandas. And in this one here, we're going to do sklearn dot pre-processing, okay, import, and this is min max scalar. Now we've done this one before in the past as well. This is when we want to scale our values into a certain range that we want. Okay, so if your sample sizes are between 1 and say 1 million, you want to try and get that down to a manageable scale that you can use in some of your charting. Next we have matplotlib import pyplot as PLT. Okay, pretty standard one. And this one here is %matplotlib inline. So I'm going to run this. You know, as expected, nothing bad happened. Okay, so now what we're going to do is just go and import that data. Okay, so we'll have data frame equal pd dot read underscore csv. Okay, and in there, what did we call it? I think it was age square feet, or sqft.csv. Okay, and then we're going to do df.head just to have a look at the data right now and make sure that it's in there. So there we are. We've got name age in square foot or square feet. Okay. And if you want to just confirm that you have everything in there, you can just take out the head and run that and go all the way down. Okay, so we've got all of our samples. Okay. And I'll restore the head part. Okay. Now we're going to do a scatter plot to have a look at this data now. And what I want to make sure you understand is when we're doing this, I'm interested in age and I'm interested in square feet. Okay. And I'm not interested in age. It's kind of irrelevant to me. It doesn't matter. And the other thing is age right now is a string. It's not a numerical value. The other thing I want to say is make sure that when you're doing this, you're looking at the data frame, you're actually doing this in a lowercase. So if you had something like this, there's a good chance you'll end up getting this error. Okay, so for this, you need to make sure that you're using uppercase for the first letter and lowercase for the rest. Okay, so let's run that. And you can see what's happening here. We've got the data plotted. Now, with the labels, it doesn't matter what you really put in there. Okay, so I've got square foot across the top, age across the bottom. So when I look at this data right now, you can kind of see the makings of 1, 2, 3, but possibly 4. And I don't know if this one belongs more to here, but just kind of visually, it looks like it's forming about 4 groups. So it's kind of hard to tell. And if you look at the actual data here, you can see that there's a couple of anomalies here, right? So 1800 and 2000. So out there, they're kind of outside the normal range of square footage, but we're going to see what happens. So what I want to do next now is I actually want to specify my K. Okay, so if I put this in here, what we're going to do is this. We're going to say KM for k-means, but we can do k-means right here. This is part of the library function, and we're saying n underscore clusters equals 3. Okay. And then we're actually doing this y predicted equals km dot fit predict df. And then don't forget, these are square brackets. I've got age and square foot. And then I just want to see the y predict, right? So if I run this, what you're seeing is this array. Now, what we can visually see by this array is that we're at 0, 1, and 2. So that is suggesting there's 3 clusters, right? Just like what we said. But I'm still not convinced about this one over here. So if I change this to 4, you'll see that this array here is going to actually update because it's now giving me 0, 1, 2, and 3. So that's giving me 4 different clusters that I can try and choose from. But for the sake of 2, just 2 dots right now, I'm actually going to keep it back to 3. Maybe we'll come back and see if there's an overall effect at the end. So I'm going to run this and I've got 0, 1, and 2 clusters. So a total of 3 clusters. Now again, I just want to be clear again, I'm ignoring our name column Here, same thing in here with my predict. I don't need the name column for anything. Plus it's a string and it's just going to create a big Python mess. So obviously looking at this and the array isn't very informative. Okay, so we do have sort of this prediction of clusters, but let's kind of visualize this in a better way. Let's go back to the table, and I'm going to put this in. And what I'm saying is create another column from my predicted, okay, and call this column cluster. So I wanted to create this sort of spreadsheet looking view and tell me which of my data points it predicts belongs to which cluster. Okay, so to show you this, let's just run that. Okay, and what you're seeing here is the first one, Rob 27, 700 square feet, belongs to cluster 1. So it's predicting cluster 1. Okay, and if you really want to see, you want to see all of it, like each one of these. Sorry, I can't get rid of the whole thing. I got to do df and run df. Okay, so what happens is when we just run df, we're looking at each and every one, and our k-mean has already done the prediction. It has decided which group it thinks that it's in. Okay, so Carol, Andre, they belong to group 0, Autumn, Julie, 1, Steve, Kira, Andrew belong to 2, and so on. Okay, so what you're seeing is the prediction's actually already been done. Okay, and I'm gonna put the head back in there so that it's just a little bit less on my screen. Okay, so there it is. And I want to, I think, look at this as a scatter plot again. Okay, I don't want to look at it in a spreadsheet. I want to look at it as an actual plot like this. Okay. But there is one thing I want to do first. I want to look at the centers of our clusters. I kind of want to see, do I actually have control of the centers of the clusters? So if I go to KM, I just type in KM, and I think equals center. Yeah, and I had that completely wrong. It shouldn't be an equal. This should actually be, let me start over, km dot clusters centers. Okay, and I want to see what those cluster center variables or values are going to look like. So when I run this, this is sort of the center points of all of my 3 clusters. Okay, so that's what that really represents. But I still want to go and look at all of this together on a scatter plot. So the way I'm going to do that, I'll go to the next cell, and I'm going to say data frame 1 equals data frame, and then in the square brackets, I'm going to say df dot clusters, or cluster, right here, cluster that equals 0. So that's saying, hey, grab my cluster called 0. Okay, and then I got to do that for my other 2. So I'm going to copy that, control V. So I'm going to say data frame 2, data frame 3. Okay, and then I'm going to just change this to 1 and to 2. Okay, so, we saw in here I've got clusters called 0, 1, and 2. And that's what we're saying. If it equals to that, then assign it to data frame 3, 2, or 1. Okay, and now we're going to do plot.scatter. Okay, and in that we're going to say data frame 1 dot age, comma, df1. And we're going to, in square brackets and single quotations, we're going to say sqft. Okay, and then we're going to go outside that square bracket and go with color equals, in single quotes, red. Okay, and we're going to do this a couple of times, 2 more times. So copy this and paste, and let's see if I can move that up. So I want 2 and 3, and then change this to 2 and then to 3. And then I'm going to change that to green and black. Okay, and then now I've got a little bit more that I need to do, because now I want to start plotting my actual centroids. Okay, I want my centroids to show up actually on the screen. Okay, so this one is going to be, let me put a note in here. Plot the centroid. Okay, it sounds like a song. Plot the centroid. Okay, plt dot scatter and then in here we're going to say k-mean or km dot cluster centers. Okay, and these ones here are going to be, we've seen this many times before, colon, not a semicolon, a colon, comma, 0. Okay, outside of that, we're going to say, again, km dot clusters centers. Okay, and then here, this is going to not be that. This is going to be, again, a colon, a comma, and a 1. Okay, and then we're going to do color. Let's see. See, if you hit the tab, you get this crazy little %. I don't want the %. I just want color without the S equals, and in this case, it's going to be blue. And then past that, we're going to do this thing called a marker. Okay, so this is how we're going to visually represent our centroid. So marker is going to be equal to, in quotations, just the star. Okay, we're just going to put that star there. And you'll see in a minute the symbol for that will appear. It'll actually look like a star on the screen. Okay, and this will be label. Label is going to equal centroid. Okay. And that centroid should actually be in a single quote. Okay. Just like that. That's cumbersome. All right. There. Okay, so we're not done. We've got a little bit more to do on the next line. What we're actually going to do is put out our labels, our X and Y labels. So plt dot X label is going to be age, and then of course plt dot Y label is going to be sqft. Don't forget the quotes, sqft. And then plt.legend, and that's just a method call. So you can leave that empty. And let's see if all of this worked. Okay. All right. So what you're seeing is a couple of different things. So we've got green, I've got black, and I have red. Okay, and note the where the centroids are. I've got 3 little tiny centroids here. Okay, so if you look at this, you immediately realize something is off. Okay, so you see that the groups are not clustered according to their color, or their color's not, according to the cluster, however you want to look at it. The issue here is this. With our age, we have a very narrow range. We go from 20 to 50. So we have actually like 30 is the range here. But in this case, we're going from 400 all the way to 2000. So the scale is off with this. And this is why up here, we talked about the min-max scaler, okay, in the pre-processing. So what we have to do now is properly scale this so that we can do this correctly. So the very first thing I'm going to need down in the next box, and I'll move it up, is a scaler. I'll just call it scaler. And we'll say min max scaler. It's a method. Okay, and now we're going to say scalar. I'm not sure I spelled that right, but I don't really care. Dot fit. Okay, and what do we want to fit into that scalar? So we're going to say our data frame. Okay, and then we'll put this into 2 square brackets. So first thing is our data frame, not those brackets, single quotes, SQFT square foot. Okay, so that's the first thing that we want to fit it into. Okay, so that's kind of the scale that we're initially more interested in, is the square footage. Okay, so the next line we're just going to say DF square brackets, single quotes, and we'll say SQFT again. And then we're going to do some transform here. Okay, so we'll do scalar dot trans. Let's see if it gives it to me. Okay, no. Transform. And in here we'll say DF square brackets. In fact, it is this here. It's literally this, but we have to change it to age. So copy this, and this should say age. Okay. In fact, I did that wrong. This shouldn't be age. That should be SQFT. Copy. That's going to be for the next line. Okay, because we're going to redo this for to fit the age as well. So I can take this and I can copy it and go down, and I can do age. I'm going to change this to age. Okay. And so far, let's just check and see that that's running okay without any errors. Okay, so far so good on that issue. Let's just have a look at it now. So df dot head. Let's see what this looks like. Okay. All right. So you're seeing this change, right? There's a dramatic change in the output of age in square feet. And so we know that the scaling worked. Now let's go and check. Did Rob change which cluster he belonged to? He's still in 1. So the first 4 were cluster 1 and Steve was 0. And so that still remains. So we've changed the actual scaling, but the clustering hasn't changed. Now, just to be careful and to be sure, what I'm going to do is run this from the very top again. And it's actually a good practice to do this sometimes, because each little cell that we're using is kind of running its own little program inside that cell, but it requires information from all the previous cells before. And I'm glad I did this, because I just noticed something. Remember a second ago, I just looked at it and I said that Steve was actually part of cluster number 0. Well, Steve just found his way, actually interesting. I ran this all from the top. And what's very interesting to me is that Steve here ended up in cluster 2, but a moment ago I think he was in cluster 0, but he's now in 2. And when I ran it from the top again, you can see that this all updated. So we should be, because we're scaling, we should still end up in the same cluster after we've scaled. Okay, so good practice. Make sure that every once in a while when you change your code or you write your code, you run all the cells from the very top down. Okay, that's how you'll get the most accurate. And I've had a number of occasions in the past where I didn't do this, and then I couldn't understand why things weren't working, and I have to go to the top and rerun it. Now, one thing I do want to do right now is I want to convert this to a scatter plot. So plt.scatter. And in here to do this, we'll say df.age, comma, df. And in the square brackets, we'll do, end quotes, SQFT. And so let's have a look at the scatter plot for this. So the big change in the plot now, though, is the scaling. So you can see where we go from 0 to 1, and then 0.0 to 1.0. So we've now modified the scaling to fit more accurately. Okay, so that's all that looks like right now. What I'm going to do is just comment that out for a minute. And now what I want to do is, now that I've done that, I've modified the scaling a little bit. I want to go back to this section up here. And I want to rerun this because now I'm doing this with a different scale. So if I just copy this and I come all the way down here and I place it in there, you can see there's a difference now, right? I've got this DF square foot and I've got this DF age. So when I have them in here, they're now different because I've rescaled them. So when I run this right now, you can see that I'm getting these predicted scatter plots, or sorry, clusters. I'm getting these predicted clusters. So I have that plotted, and now I just want to do, I want to look at this in a more of a spreadsheet format. So if I put in our DF cluster equals Y predicted, and then just look at the first 5. Okay, so what have I got? I've got, name, age. Again, you can see they're all newly scaled. Okay, so age is not the numbers it used to be. Okay, so it's newly scaled, and we've got a prediction of the cluster. So if I take this out and I rerun it, you can see all of the values. Okay, and I'll just rerun that. So next thing I want to do is I want to see this on a scatter plot. So I'm literally just going to go up to here, what we had before. I'm going to grab this stuff, come back down and drop it in there. Just for now, I'll take this. I'm just going to take this out just for now. And let's have a look. Okay, so now you're seeing 3 different distinct clusters now. And that has largely everything to do with how we rescaled it. Okay. So let's go have a look at the centroids again. So if I go back up to this cell here and it's blue, and I type in B, I get a cell below. And we wrote this code before, right here. Let's look at our cluster centers into that cell that we just used, and let's run that. Okay, and what we're getting is the actual centers of each of our centroids, or the center of the clusters is where we're going to drop the hopefully drop our centroids. So let's update this here and now start plotting our centroids there. And the way we'll do this is plt dot scatter, and here we're going to do a bracket, and then in this bracket we're going to say km dot cluster, and we'll do the tab. It gives us cluster centers, and it's square brackets, and we've done this one before, so it is a colon because the first space is empty. That's to say get all of the rows. Okay, and now what I want you to do is select 0 so that we're taking this center here. Okay, so that's the one that I want right now. And you're just going to really repeat that. Copy, put a comma, and to get the first column, we're literally going to paste that in and change this to a 1. Okay, so this is first row and column. So that's what that syntax means. And I want to still do more of this, okay, because I want to actually add a label in some colors. Okay, so after that, we're going to go with a comma, color, and it's color without the S, so it's singular color, and we're going to say that it's going to be blue. Okay, and that's in brackets. Marker is going to be equal to, Now this is single quotes with a asterisk or a star. Okay, and then a comma, and I want to say S equals, so for scale or size of it, let's say 200. Okay. And then finally we have a label. And the label is going to just say in not double quotes, single quotes, Centroid. Okay, and then we should be at our the end of our bracket there. So go back to here and we've got legend, and let's see what happens when we run this. Okay, so now what you're seeing is the blue stars are the centroid of each of the 3 clusters. Okay, so we're really in good shape here. Okay, and of course these blue dots are represented by the cluster centers. Okay, so if you plotted those out, that's what you would find would be each of these. So if we even look at the first one, 0.25, 0.25 right here, and then 0.13. So yeah, that's the first one there. The second one being 0.73, somewhere over here, and 0.71, which I guess is going to be this cluster right here. And then finally, the last one would be, 0.17. Right down here. So those are, we're just plotting out those, and I'm using 200 really for scale. I could change this to a 1, rerun this, and you'll see they'll get significantly smaller or half the size. So in essence, we're really kind of complete with this. Okay, we are done the example. We've got 3 different clusters of things that we might have been trying to decide. And now in this example, we didn't exactly specify what we were looking for. We are just trying to use some information to reveal some sort of patterns in a sense. Okay. And then you can make sort of a deduction later on with what this information reveals. What do these clusters represent to you? Okay, and in this example, we're not really specifying much other than to say that, hey, based on your age and the square footage of your home, it is likely to represent something. Say maybe it's a part of the Greater Toronto area, or let's say it represents something about people that all work for a company. Okay, the older they are, the longer they've been there, the more salary that they're getting, therefore they can afford a bigger home. So you're kind of making a deduction based off of what you're seeing in the scatter. Now, let's just quickly shift gears now and talk about the elbow technique, or the elbow. Okay, so I want to kind of be able to plot that on the map. And it doesn't really matter here, but I want to see if it proves that 3 was probably the best cluster we could have gone to. So what I'm going to do is elbow plot. Okay, and I'm going to actually change this to a markdown. I'm going to run that. It's more of a title. In fact, I could change this to a heading. Okay, run, and we're good. So now what I'm going to do is, take care of this issue. So I've got my WSS and my number of clusters, and I'm going to try to determine that best point, or that elbow. Okay, and my concern here is that it's not going to be like the perfect elbow. It's not going to be crystal clear, because my sample size was rather short or small, and you could see these outliers around the age of 48, 49, and 50. But let's go and have a look and plot this out and see what happens. So I'm going to start with WSS equals. This, just going to put the brackets in for an array. Okay, and we're going to say K underscore RNG for range. Okay, and that's going to equal range between, say, 1 and 10. 1, comma 10. Now I'm going to do a for k in k underscore range. Okay, and don't forget the colon at the end. It'll help with your formatting because it's a for loop. So it'll be km equals k means, capital K means put in your tab. Hopefully it pops up. Doesn't seem to be so far. K means, and in here it'll be n underscore clustering clusters equals k. Okay. Now go down to the next line. All right, what's going on here? My k, I would have thought my k would have, okay, no, we're okay here. We're fine. So we'll do km dot fit. No, not for, fit. And in here, we'll say, df square brackets, no, not that way, inside, square brackets, and we're gonna say in single quotes age, comma, single brackets, sqft. Okay, and that looks fine. Next thing we're gonna do is wss dot append. Okay, and then we're going to use this thing called km dot inertia. Okay, and then underscore. Don't worry about what that is. You just need to know that in order to run this, I need it. Okay, so I've got one error. And so looking at this error, my guess is it's just not picking up the k-means, because I probably hadn't run it from a previous, we'll see. It's looking for k-means. I'll just go back all the way to the top right here, and I'm just going to run it to the very bottom, and you can see that the error actually went away once I did that. And this is what I was, I always have to caution you that that's an issue, right? These cells are little micro programs or subroutines that need to be run in order for the next cell in the sequence to pick it up. So what I want to do now is just plot this. So I'm going to plot this. X label is going to be K single quote, capital K. All right, and then plt dot Y label. Okay, and this one is going to be, it's going to just say sum of squared error. Okay, I'm just going to leave that there. Okay, and then the last thing is going to be plt dot plot, and then our two arguments there, which is going to be k underscore range, comma, WSS. Okay, so WSS. And that should be it. Let's have a look and see what this looks like. All right, so here it is. Okay, and you can see in the elbow, this is what I was talking about. We've got kind of a natural break there, but we're still turning. Okay, and then we come to 3, and then we have a slight sort of turn there. Okay, and there's a little bit one there with 4. So, I think the most, to me, the most drastic kind of turn was maybe 3. So I'm going to stick with that because I don't see the big value in changing it to a 4. And if it was a drastic bend in that elbow, then I would go back and change it to 4. But keep in mind, I would have to in order to plot this, I'd have to add a df4 and all that kind of stuff, right? So for now, I'm happy with that because it's close enough to me. Okay, so even if, let's say I went up here, this is probably going to just throw an error. If I change that to 4 and I try to run all this, You know, it's drastically changing everything for sure. And all you're seeing is a centroid way over here in the corner, right? And if you can remember, we only had 2 points over there. So if I look at a different, we had these 2 points over here. And I don't think that that's enough to constitute really a very definitive cluster. Okay, so what I'll do is I'll put it back to 3, and I'm going to stick with 3 because I think that's pretty reasonable, given all the data set. Okay, and it's a very small data set, right? Now, keep in mind, what if you had, you know, 20 to 30 different features that you were trying to compare? Okay, so you've got to consider that as well. All right, so if you had a large group and you went through this whole process and your bend in your elbow was in a totally different location or was totally something different, you would, to optimize it, go back and change your K value. Okay, but in this case, we really only have 2 features that we're really looking at, and it's a very, very small sample size, so I'm not going to change it. I wouldn't. I don't think it's really worth it. Okay, so anyway, that's it for this video. Thanks for watching, and I'll see you next time. Thanks.